Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
That's us. Hi, everyone. I'm Dr. Moiya McTier. I'm an astrophysicist and a folklorist and a friend to the universe and many who inhabit it, like
Indeed.
my co-host.
That's me. I'm Connie. I am friend to the universe, friend to Moiya here, and I'm curious about what we're going to talk about today. Bestie?
Yeah. Well, we've been zooming in so much lately, going down to the quantum scale, talking about particle physics, talking about the Large Hadron Collider and their particle collision experiments. I thought it might be nice and or
You were going to say
stressful.
fun, weren't you, Bestie?
No. So either nice or stressful in a different way.
Okay.
To zoom out, to go in the opposite direction and start thinking about the largest things out there, or the largest thing, which, as far as science has defined, is the universe that we all inhabit.
Yeah, that's pretty much the whole thing, right? Huh? Maybe.
Maybe.
Okay.
Good catch.
Okay.
Yeah. So this is a hard episode for me. Cosmology was one of my more difficult subjects that I took. It's cool conceptually and I like thinking about it, but the equations that are involved, it's a lot of like multivariable differential equations and like high order math stuff that I did, but I didn't like it. So we're not going to be talking in detail about any of those equations today. Don't worry. But just the concept of what the universe looks like, maybe from like the outside in, or like at least from the edge in.
Okay.
And what edge even means in this context.
Yeah. This is going to be one of those brain wrinkling episodes. Let's buckle up, folks.
Do you have any questions or any concerns right off the bat? Because I can see you have the thinking face.
I have the trepidation face because I'm just like, wow, that is such a, as I've said before, it's like, it is brain wrinkling because I'm just like, yeah, the edge of the universe. And just like, my brain already starts tingling. Like, what is that? Like, I can't picture it, but I kind of can. But I feel like there's like a wall behind me of coldness. Like I can imagine looking in at the universe, but there's this like tingling, like TV static sensation behind me because it's like, what could possibly be beyond the edge of our universe? And that is like, whoa.
That visual is really interesting. So are you thinking of the universe in a unidirectional type of context? like we are one end and it goes out from us?
Maybe.
Instead of a more spherical view of the universe that goes out from us in all directions.
It goes out from us in all directions, but perhaps a dome. Like I can see like the idea of looking at the universe and it like all the stars being up and down and left and right and forward. But then behind me is just like, I don't know. It's like a muffled sensation of just like,
there are more stars back there, I promise.
But at the edge, that's what I mean.
Oh, so not behind you directionally,
yes,
but
like I'm
far away from you in all
edge.
Directions.
Yeah, like I'm pressed up against what would be maybe the edge, and like that's like I can only ever see in front of me, but I can't like turn around anymore.
Okay, yes.
Yeah.
If you yourself are at the edge and not looking from
Exactly.
our vantage point on Earth.
Exactly,
okay.
yes.
Reference points are so important in physics and in conversations about space.
Indeed.
I should have specified where your point of reference was. Okay. But yeah, I want to zoom out from Earth today. I found this gorgeous illustration by Pablo Carlos Budassi. That's his Instagram handle. And it starts at one end with the Earth and then zooms out to basically what is the observable edge of the universe. And so the stuff nearest to the Earth's atmosphere, and then all of the satellites that we've launched into our orbit, and then the rest of the solar system, the Oort cloud, and then we're talking other stars in the Milky Way, zooming out to other galaxies entirely. And then by the time you're zoomed out really, really far, because, you know, one of the consequences of a finite speed of light can only travel so fast. The farther away we're looking from us, the farther back in time we are peering, because it takes that light time to travel to us.
Right.
So we're seeing it how it was all that time ago when the photon was first emitted. So astronomers are time travelers.
Yeah.
In our brains, at least. And by the time you get to the other end of this image, you're talking about the time in the universe before there were stars, before there were neutral atoms. It goes all the way back to what astronomers call the surface of last scattering, which is where the cosmic microwave background originated. That is the moment in time. Notice I say moment in time and not place in the universe. The moment in time when the universe cooled down enough to let electrons bind on to the nuclei where the protons and neutrons had already gathered. And because there weren't all these free-floating electrons around, the photons could escape and show us how the matter was distributed at that moment in time. So that snapshot in time then becomes known as the surface of last scattering. So we talk about it as if it is a place, but it's not like we can pinpoint where physically in the universe that was, because back when that light was emitted, when that signal was created, it happened everywhere in the universe.
Okay, bestie.
Yeah, I can tell you have so many feelings and reactions.
So many feelings and reactions, because I'm looking at this image and it's like vertical down, and it's so crazy to think about. And then my second thought was, wow, this is so cool, because I can never figure out how to illustrate this. And Pablo has done it so well. Like the way that the particles that he's expressed scattered. And then I'm looking up Pablo Carlos Badassi, and he's done it in a circle. And so if I imagine myself in the circle version of this, that the way it scatters is like the static that I can feel just surrounding me, where I'm looking in at the universe as pictured from the bottom of the vertical image and from the edge of the circle in the round image. And that is the static.
Bestie, I'm about to blow your mind.
You've already done it, bestie.
This stuff at the bottom of this image from Pablo is the cosmic microwave background. It is the surface of last scattering.
Okay.
And that signal, that microwave signal, is actually what caused static on old-timey TVs.
Wait, what?
Yeah, so your mental metaphor is perfect.
Okay, but how?
Because it's a constant source of low-grade microwave noise.
And it just, because it's the antennas and stuff are picking it up.
Yeah, they're picking up a broad frequency.
It's light.
Because it's all light.
Okay.
Yeah, you're doing great, bestie. I'm so proud of you.
Thank you, because I feel, for anyone who's seen Backrooms, I feel like I'm about to go into the Backrooms, because it's very much like that nostalgia of the 90s that movie evokes, but going to a new idea of static electricity in the TV being connected to traveling through, there's just some cool connection there where you can make a cool story there.
When we get close to the static, when we get really far away from Earth and we're peering really far back in time, we don't really use distance values in astronomy by the time you get out that far. We're not usually measuring things in light years or parsecs. We can do that conversion, but often when astronomers are talking about really, really distant objects, they will give you its redshift value, specifically cosmological redshift, because there are different types of redshift. I know you've heard of the Doppler effect.
Yes.
And we've talked about the radial velocity method for finding exoplanets, where you're seeing the stars wobble. The way we detect that wobble is by looking at the spectrum of the star and seeing it shift to the left, shift towards the blue when the star is coming towards us, and shift towards the red or to longer wavelengths when the star is moving away from us. So by how much it shifts, we can figure out how much the star is wobbling and therefore how massive the planet around that star must be.
Ah, okay.
So those are types of redshift. The general concept of redshift is all about how light waves emitted from a source object get stretched when that source object is moving away from us. And cosmic redshift or cosmological redshift is that general concept, but on the biggest scales of the universe, because the universe is expanding. We discovered this in the 1920s, thank you, Edwin Hubble, when he was looking at distant galaxies, what we had just figured out were distant galaxies, by the way, instead of just distant star clusters within a giant Milky Way galaxy. Hubble was looking at distant galaxies and realized that the farther away a galaxy is, the more its light is redshifted. So the faster it is moving away from us.
Yeah.
So the universe is expanding. All of the galaxies that are not gravitationally bound to each other, so like in their own little galaxy clusters, they are being carried away from everything. It's not like away from a central point. The Big Bang did not happen at a point, at like a place in the universe, but instead happened everywhere at a point in time when the universe was small enough that like everywhere was just this tiny, tiny point.
Bestie, it also, is it because we generally just aren't in a specific place in the universe? Like the universe isn't static in a place. Is it also moving? Like the whole thing is moving?
We don't have any sort of reference frame for outside the universe. But all of the galaxies in the universe are moving. But that is not what I'm talking about when I'm talking about cosmological redshift. These galaxies are not moving away from us. They are being carried away from us by the expansion of space itself. So this gets us into a tricky position, kind of, because the most distant objects that have a lot of space between us and them, that's a lot of opportunity for expansion. And so the most distant objects are actually traveling away from us faster than the speed of light. But that's not breaking any physical rules because the galaxies themselves are not moving through space. They are being carried along with space, which is expanding, not faster than the speed of light, but every zone of space is expanding. And so if you have more zones between us and some distant object, that's just a bunch of expansion. That adds up.
For sure.
So because of this, the redshift, which astronomers will denote with a lowercase z, an uppercase z is used to denote metallicity, which is like how many elements heavier than helium are present in an object. But that lowercase z, redshift, is a proxy for distance. And it has no unit to it. It's just like a unitless value. And you can calculate an object's redshift in a few different ways. You can measure an object's redshift in a few different ways. Like if you have a spectrum of the object, you can measure its redshift sometimes. But you can also do this mathematically with something called a scale factor. This is another unitless value. So it doesn't have like kilometers or seconds or like any type of unit associated with it. It's just a scaling value that you can use as something that describes the size of the universe at a particular time.
Okay.
This was thought of in the 1920s, 1930s when people were developing their mathematical models of how the universe works. But just to give you like the math of it, the redshift is dependent on the ratio of the scale factor of the universe now, like when we get the light from the object, and the scale factor of the universe when that light was first emitted. And remember, the universe has been expanding, so early on it was smaller, so it has a smaller scale factor. So that means if an object is farther away and the light coming from it was emitted at an earlier time, the ratio is going to be really big from the scale factor now to the scale factor then. So you have a bigger redshift. And the farthest thing we can see, that surface of last scattering from the cosmic microwave background, that has a redshift of 1100. So that's the scale here. The object's really, really close to us. Like anything within our local group of galaxies out to Andromeda, we don't bother talking about redshift because it's bound to us. It's not even being carried away by dark energy. So like a nearby galaxy cluster, we still probably wouldn't even use redshift values because they would be so close to zero. It's only when we're getting out to many billions of light years away that we start talking about things in terms of redshift.
Gotcha.
I guess we've already talked a little bit about this when we went through the picture, but I do want to discuss like the large scale structure. What does the universe look like when you zoom out? Not all the way to the edge, but on the way to the edge.
Okay.
So we have the Big Bang Theory, which was proposed in the 1930s and says that the universe started from a primeval atom, from this tiny, tiny point, and then it had an inflationary period where it got really big and all of the matter and energy that was contained in that tiny point expanded and moved up away from each other and cooled down rapidly. And then the universe continued to expand more slowly after that. But based on that model and also based on observations, when we look into the distant universe, we can tell that the early universe was less structured. So not all of the gas and material had been coalesced into stars and galaxies. So there was a lot more just like free-floating gas and dust. Mm-hmm. The galaxies that did exist were smaller. They were mostly hydrogen and helium, like even more than modern day galaxies, because they didn't have time for the heavier elements to form and enrich the space. They were also bluer, so that like they had younger, heavier stars, younger, more massive stars, and higher star formation rates, and more spiral galaxies than elliptical galaxies, which makes sense because ellipticals are typically formed when spiral galaxies collide and stick together. The galaxies back then were also a lot closer together and had more gravitational interactions with each other. And so they seemed more evenly spread out in the space than they look now, but that's just because they were packed so tightly together. There were actually tiny differences in density from one space to the next, and as the universe expanded, those tiny little over and under densities got exaggerated, so that the over densities through gravity continued to acquire more stuff, and the less dense spaces, they didn't have the strength of gravity to attract stuff, so they were probably attracted to other nearby, more gravitationally influential sources. It's capitalism, but with mass instead of money.
It also just reminds me of like your group of friends in high school and how a lot of times okay, you're packed together in the school, you're friends because of proximity, and then you kind of move away and separate, and your universe expands, and you have more things in your universe, and you're farther away from your friends, but not necessarily not still close, but you're just moving farther away. But then some uninteresting galaxies or some unmotivated galaxies are just swept up by maybe family life at home or a particular relationship or something, and they kind of just stay over there and merge with somebody else's galaxy, as opposed to kind of continuing their own and going off as just a metaphor for what we kind of do now. You go off to college and you're supposed to expand your life, but in the olden days you kind of did work at home and stayed close to home. So it's just it made me think of people. Especially because I was thinking about the Milky Way and Andromeda and their relationship.
Their epic romance. Yes, yes. That metaphor really worked at the beginning. That was really good.
I'm sure it fell apart at the end, but it's fine.
But it's not. It's a nice sentiment. Yeah. So we can tell based on models and observation that is the case. That the farther back we look, the less structured the universe is. One of the big sources of observational evidence was a 1985 redshift survey at the Harvard Center for Astrophysics. And in 85, they started this 10-year survey where they studied 18,000 galaxies in the northern sky. This was the second time they did that. They did a first round in the 70s, and that was apparently the first coordinated effort to map the large-scale structure of the universe. Thank you, Harvard. And what the 1985 survey showed after, they completed their work in 1995, a great year, was that galaxies are not distributed evenly, but that they are gathered together on the surfaces of invisible bubbles, of voids out in the universe. So that there are these big bubbles of empty space, and all of the galaxies are gathered along the edges of those bubbles. Or another way to think of it is that all of the material is gathered along these long, stringy filaments. And then there are a lot of empty spaces in between the filaments. And the connecting points for the filaments are massive galaxy clusters that are using their gravity to attract other material along these filaments. This is what we call the cosmic web, which was a term introduced by John Richard Bond, who unfortunately goes by Dick Bond. And he was a cosmologist and a professor at the University of Toronto. And in 1996, he published a paper called How Filaments of Galaxies Are Woven into the Cosmic Web. So he now has access to this redshift survey data, and he's seeing, along with other researchers, that filamentary structure. I don't know if that's actually like the word that I'm looking for, but I'm just going to go for it. Filamentary. And this is 30 years after we'd discovered the cosmic microwave background, but we'd been studying it. We'd been trying to map it, figure out its potential uses. And after Richard Bond saw that data in the distribution of galaxies, he started theorizing how the anisotropies, the tiny little differences in matter density in the cosmic microwave background signal, could grow to be these galaxy cluster filament and then void structure. And this was confirmed by even more observations later. There's also some cool science that we've done, some very creative science that astronomers have tried to do to study this large-scale structure. In 2020, there was a team from UC Santa Cruz that wanted to map the filaments in the local universe. That's within about 500 million light years of us. So it includes like the Virgo cluster of galaxies and like all the nearest galaxy clusters. So you would imagine that there should be a lot of filaments connecting these galaxy clusters, but they're made of mostly hydrogen gas with some helium gas thrown in. They're really faint, so they're hard to see. And space is really big, so we wouldn't necessarily know where to look for them. But this team from UC Santa Cruz, they developed a computer program that was inspired by slime mold growth patterns. Really, just
great job, nerds.
looking for inspiration wherever we can find it.
There was like a environmental science or somebody like who was just around, like they were like,
Yes.
Wait, what about mold?
Like someone had an elective and then they used this in their work. Yeah, absolutely.
Yeah.
I love this. It helped them see where the filaments should be because they developed the program to see how the slime mold decides where to grow. And then into that program, they put the location data for a bunch of different galaxies in the local universe. And then they had the program connect them via filaments. And then they looked out in space where the program said the filaments should be, and they were able to find it.
Wow.
Yeah. They did that by waiting for light from a quasar. I think we've talked about quasars before, right? Do you remember what they are?
No, because then we talked about quantum and quarks, and so they've gotten a little mixed up.
A quasar is an energetic black hole that is shooting out jets of light that we can see. And like the light will pass through gas and other stuff in the universe, and that will change its signature as parts of the light are absorbed by molecules in whatever it passes through.
Right.
So these researchers were able to tell that the quasar light was passing through this filamentary gas.
Oh.
Success.
We love interdisciplinary thinking.
Yes, we do. And we love more direct thinking as well.
Absolutely.
Which, we can do with the improvement of technology, like JWST, the James Webb Space Telescope, or Jelly Welly Space Telly.
As we call it.
It has been peering far back into the universe and into time to map the large-scale structure with its, I think it's the longest or like the biggest general observation program that JWST has had, and it's called Cosmos Web, which is maybe one of the most mangled acronyms I've ever seen. Cosmos is the Cosmological Evolution Survey. Actually, Cosmological Evolution Survey.
Yeah, no.
And then web, just because it's looking at a web-shaped structure.
No, they didn't even try to get evolutionary in there.
Yeah.
You know, earlier you talked about the scattered light at the end of
The surface of last scattering.
The surface of last scattering is so poetic and like a little fantastical. Like, do you remember the surface of the last scattering? But then you go, Cosmos Web stands for Cosmological Evolution Survey. There really is a variety in every field, but especially, but even science.
Yes, it takes all kinds. I mean, despite its name shortcomings, this is a really cool project. They're looking at a patch of the sky about the size of the full moon, a little bit larger, for more than 250 hours. And in May of this year, they put out a paper showing their newest map of the structure of the universe. It has 164,000 galaxies mapped in it. It's the most detailed map they've put out yet. It's actually so detailed. There's so many data points that you can't see much on like a single picture. Like you have to zoom in and do other types of analysis. But what you can see in this image, which I will remember to post on Instagram, is that as you go farther away from us and therefore farther back in time, the density of galaxies decreases. Do you see that in the image?
Yeah. It's like it kind of looks I'm not going to say solid because there is like scattering on the edges and some in the middle, but like it's kind of a very close, dense thing. And then like it starts to dot out really towards the edge. It's very cool. It does remind me of stars. It shows what it shows.
We love when plots do that. Yes. Mm-hmm. Hi friends, it's me. Connie is using the department's special fast zoom telescope to count galaxies in the early universe, so I have a couple minutes to share some messages with you. And the first message is of course going to be a thank you to all of the patrons who support the show financially every month. We're an independent podcast, so we couldn't continue to make this show without your support. Thank you all so much. And we want to give a special shout out to our Sun-like stars, Scott Reynolds, Tom T, Seven Petrichor, Ashley Shambo, Bruce Sedloff, and Kelly Bennell. Thank you all so much. We appreciate your support more than you can know. If you want to join this stellar group of people and hear your name on the show, you can do that by signing up on patreon.com/palebluepod. You'd also get a spot on the patron star chart and get research notes for pretty much every episode. All of that for $5 a month at patreon.com/palebluepod or the link in the episode description. You could also make a one-time donation at the PayPal link in the episode description if a monthly subscription isn't for you. And if you can't support us financially at all at any time, we understand. We make the show for everyone because you're all space and we love you all. There are other ways that you could help the show grow if you feel so inclined, like rating and reviewing the show on whatever podcast app you prefer and sharing a link to a specific episode with someone who you think would enjoy it. But no matter what, Connie and I are honored to be a part of your week, so thank you so much for listening. My next message is about our merch. You can order it now at certifiedcrucial.com/collections. Look for Pale Blue Pod. That link is also in the episode description. I'm wearing the t-shirt, the Eat the Sun t-shirt right now. It's really comfortable. And I just got a sample of the blanket from the artist we're collabing with, K', and it's beautiful. So check out our merch. You can buy it now. And by the time the blanket gets to you, it'll almost be the fall. So it'll almost be chilly blanket season. My next message is a recommendation for another podcast in the Multitude Collective called Wow If True. This is your one-stop internet culture shop explaining how what's happening online shapes the real world. The hosts are the internet experts and real-life besties to unravel it all. One is tech culture journalist Amanda Silberling, and the other is science fiction author / legit attorney Isabel J. Kim, Esquire. They are the only podcast that will mention Neopets and horizontal mergers in the same episode, so check them out. They're asking and answering your burning questions about the internet, like why are the edgelord tech bros literally everywhere, even in the White House? And is Pepe the Frog a hate symbol or just a misunderstood green guy? They just did an episode about the enhanced games, which, if you haven't heard about them before, are the Silicon Valley version of the Olympics, where they let people take performance-enhancing substances to see how far we can really push the human body. I think this sounds kind of gross and definitely ethically dubious, but scientifically interesting. So if you want to learn more about it like me, then listen to the episode. You can check out Wow If True wherever on the internet you find your podcasts. New episodes come out every other Wednesday. Okay, Connie is done counting now and can confirm that the galaxies in the early universe were indeed smaller and dimmer and less dense. There were fewer stars and more gas between the galaxies, so now that she has really cemented that knowledge, we can focus on even bigger scales. Let's get back to it. So that is the large-scale structure of the universe and how we know about it. That's all of the stuff that the universe holds. What about the structure or the shape of the universe itself?
Yeah.
Hold on to your wrap. Hold on to all your clothes.
To your butts.
All right. So when we're talking about the shape of the universe, remember, we're not just talking in 3 dimensions. We're talking in at least 4 dimensions. And so it's really hard to picture. So I'm going to say things like sphere or flat plane, but these are special geometry terms that get weird at 4, 5, 6 dimensions. Okay, so a flat plane in geometry, when you're talking about more than 3 dimensions, could actually be like a cylinder.
Oh no.
Because there's specific definitions of flatness that we will go over, but I just wanted to warn you.
Thank you for the warning, bestie.
You're
Thank
welcome.
you.
It's because I love you. Yes.
Yeah, I feel it.
And I appreciate you being here learning about this.
Yeah, I'm doing my best.
You are. I'm so proud.
Thank you.
Okay.
So we're going. Let's get wild.
Let's get wild. We're going back to Einstein.
I know him.
Great. Personally? Imagine. Shortly after he published General Relativity in 1915, he and other scientists were working on understanding what that means for the actual physical universe. Because special and general relativity were about how matter interacts with space-time under the influence of gravity. So how can gravity curve space-time? And then once we understood that concept, we could look out at the universe and try to figure out how is the matter in the universe curving the space-time of the universe? How is it actually practically affecting the universe? So Einstein published his field equations, which is a group of weird, complicated differential equations with many variables, but they describe how matter and energy interact with each other under gravity and the different forces, mostly gravity, to affect the shape of space-time. Those equations are just that. They're not solutions. They can have multiple solutions to them mathematically. So other scientists came along. There are names like Alexander Friedman, George Lemaitre, and there's a Wilkerson, there's a Roberts. There are a bunch of people who work together and on their own to develop different mathematical models of the universe that will solve Einstein's field equations. And all of the models vary in terms of how they distribute dark matter, baryonic matter, dark energy, and radiation, which is like photons and neutrinos. So there are a bunch of different models, but we have keyed in on some main characteristics. The Big Bang Theory wraps up in it like a specific model of the universe with specific features. Mm-hmm. One of the values that we're interested in with all of these different models is something called the critical density of the universe.
Okay.
And it's like matter and energy together, because Einstein taught us that those can be exchanged. But the matter-energy density of the universe, the critical density, is the density that the universe would have if it were going to expand and then stop after an infinite period of time, but not contract back in on itself. So it's like the perfect balance of the universe continuing to expand forever and is ripped apart, balancing that with the universe will crunch back in on itself after it stops expanding.
Yes, we did do an episode about that.
Yes. So you have to hear things multiple times and in different contexts.
I really do. So I appreciate it, Bestie.
One does. I was like, one does. We all do. If we can measure the density of the universe with different components, like the total density is the density of dark matter plus the density of dark energy plus the density of baryons and stuff like that. If we can measure the total density of the universe and it is less than 1, right? There's like a ratio in there. But if it's less than 1, then what we have is a closed universe or a hyperbolic sphere of a universe, which looks like a saddle shape.
Okay.
Where like there's a valley, but in multiple dimensions,
Okay.
Yeah. Okay. Like the valley in one direction is the hill in the other direction. So it's this weird geometrical shape where if you were to send off 2 beams of light that are traveling in parallel lines, under this geometry, those parallel lines will always eventually diverge. They'll move apart from each other.
Interesting.
But that's not what parallel lines do
in
a flat geometry, which is what we would have if that critical density is equal to 1. So in this scenario with a flat universe, you set off 2 parallel lines of light. They will never meet. They will carry on. And then you end up with a completely flat plane. If the critical density is bigger than 1, you end up with an open spherical universe where if you shoot off 2 parallel lines of light, they will always eventually converge. They will always cross.
Yeah.
The data suggests when we add up the density of all of these different components, matter and energy, the data suggests that the density is the critical density. So it seems to add up to almost exactly 1. So it seems like energy and matter are distributed in the universe in such a way that it will expand but stop after an infinite amount of time. And that type of coincidence, like, it just happens to add up to this perfect critical density value, that is what we call the flatness problem.
Okay.
And the only solution to this flatness problem is to collect more data and figure out what the shape of the universe is at bigger scales.
I hope they're on it.
Yes. But even though I say the universe, according to the data we've collected so far, is flat, that doesn't have to mean it's infinite, right? Because a flat plane can go off forever. You can also have a geometrically flat plane, imagine like a piece of paper, and then round that paper back on itself so that it makes a cylinder.
Okay.
If you shoot off 2 parallel lines, those parallel lines will never meet. So that surface is still geometrically flat, but it is finite.
Yeah.
Because the paper is rounded in on itself. You can't move off forever in every direction.
So we're inside of the paper fold.
Well, this is just hypothetical. Like these are different. Like we know the universe is flat, but we don't know what type of flat.
Yeah. Okay.
And in that scenario, it's not like we're in the tube then created by the paper. Not like hovering in the space. We're in the paper.
Oh. Okay.
In the paper itself. Yes.
Okay.
Bestie, I know that you are doing your best to absorb this information and that it's really blowing your mind because there have been multiple omega symbols in our notes and you haven't said anything, not a once. You are focused.
I am focused, bestie. I'm like, okay, omega is less than 1. Or it's flat, but then 2 parallel lines. I was really focusing on the parallel lines and how they would converge or separate. So, yeah, I was focused. Listen, I'm in my peak Greek era right now because of the Odyssey. So, I peeped
Greek
it.
stuff.
I peeped it. Yeah, like I
Greek
went back
stuff,
to
yeah.
Greek stuff. Yeah. What were you thinking, bestie, for the omega symbol? Oh yeah, that. See, I didn't even, that's how you know I'm focused. That's really how
exactly.
You know.
Exactly, bestie. I even hinted at it, and it still took you a minute to get it.
I was so focused on those parallel lines. Like, okay, if it's a closed universe and a hyperbolic sphere, diverging parallel lines, they'll separate. I was really doing the finger motions and everything. Like, okay, let's see, how do we do this?
There are some really great illustrations online. I saw one with 2 space slugs firing off laser beams.
Nice.
They're great out there, but good job on your focus.
Thank you, bestie.
So now that we've talked about the shape of the universe and the fact that it is flat, but we don't know what kind of flat, now we have to imagine, just have a kind of philosophical discussion.
Okay.
A kind of philosophical discussion about the edge of the universe. What does it actually mean? Well, I'll tell you that the edge of the universe is a boundary in time and not a boundary in space, just like the Big Bang is a point in time and the CMB, the surface of last scattering, is a moment in time and not points in space.
Okay.
So the edge is a boundary in time, and every single spot in the universe has its own individually defined edge. If we were to travel to the Virgo cluster of galaxies, for example, it's something like, 50 million light years away, we would have a different edge to the universe because we would be in a different reference point and we would be able to see further in some directions and not as far in others. So the observable universe, the edge of the universe, is defined as a bubble around wherever you, the observer, happen to be.
Oh.
And if you're being a real stickler about it,
which we know people are these days about a lot of things,
it is also kind of about how long you've been observing in that space, too.
Great. Another dimension.
Yes. So a few things to think about when we're discussing the edge of the universe. We have to remember that the distance to the object when that light was emitted is not going to be the same as the distance to that same object now, because it has moved on its own. Because you're right, everything in the universe is moving, but it has also been carried away by the dark energy expanding the universe.
And if 2 people were observing the same object from here and from the Virgo cluster, the numbers would be different because of the different places and time locations?
Yes.
Okay. I'm glad I can understand it, but can I accept it? I'm working on it.
So I pulled a couple of quotes just to demonstrate how kind of mind-fucky this can be.
Yeah.
Okay. So this is admittedly from Wikipedia.
I love her.
When we look back to distances of 19 billion light years,
sure,
that corresponds to a time when the universe was just 3 billion years old. Remember, the universe is about 14 billion years old.
I did need that reminder. Thank you, bestie.
Okay. But as we close in on 27 billion light years away, which is a real distance we can observe, the universe was only 1 billion years old. At 27 billion light years away, when we're peering 27 billion light years away from us, it's not actually peering 27 billion years into the past because the universe isn't even that old.
Right.
So in some ways, we're even like more time travelers.
Yeah, because this is like going back to before the event that you are even trying to go back to.
Because you're only seeing things that happened 13 billion years ago.
Mm-hmm.
But you're seeing it 27 billion light years away.
Okay. Mm-hmm.
Mm-hmm. Mm-hmm. Because that object has been carried even farther away from us since it emitted the light.
Yeah.
Okay, so that's something to keep in mind, that we have to remember these things are moving. So these, like if you're on a trip, you're going on a girls' trip, and you call your friend in the morning, you're like, where are you? You have to remember they're moving. So if you call them again 2 hours later, like they're going to be in a different place.
Yeah. That actually is a funny little overthink that people do about time travel stories, where it's like, well, if you were really doing the time travel right, because the Earth is moving and because space is expanding, if you went back and it was like a single point in time, like you would end up like in the middle of space because, oh, we've moved. And so you'd end up in the same place, but like in space, not on the planet. And it's like, okay, you're going, you're overthinking it.
One of my favorite factual inaccuracies in Stargate is that the Stargates were put in place thousands of years ago. Mm-hmm. And when the Stargate program starts up, the addresses don't line up perfectly. Mm-hmm. And they explain it as the expansion of the universe has shifted the positions of these stars. But no, because the expansion of the universe only acts outside of gravitationally bound context. All of the stars in the Milky Way are gravitationally bound to each other. They are moving. They're going to like deviate from their original positions because of their own proper motions, but it has nothing to do with the expansion of the universe. And sometimes an inaccuracy is just like so salty goodness. It's like,
especially when it's something when it's someone who thinks that they're like solving an inaccuracy or like addressing like, oh, well, it wouldn't really work that way, so I'm going to change it from how people usually do it. And then it's like, okay, but you're technically still wrong.
Yeah, like, but at least you're trying. Thank you.
At least you're
trying. Okay, yes. So we have to remember these things are moving. Another dichotomy that I want you to keep in mind is the observable universe versus the reachable universe.
Yeah.
So the observable universe is like their light can reach us. So information from them can reach us so we can observe it. The observable universe is technically growing by 1 light year each year because, as time goes on, that light has had the opportunity to reach us now. But the observable edge of the universe is moving away faster than the speed of light. So really, it's like we're gaining space but losing information.
Yeah.
We are making ground, but we're never going to catch up with it.
Dang.
That's one thing. That actually never catching up with it is the reachable universe. So the reachable universe is the boundary within which our light can reach them, or like we could send information to them, or if we manage to travel at the speed of light, we could physically get there. Okay. And that is harder to calculate because it's like, we could reach them eventually. So it depends on the future behavior of like dark energy and whether the universe is going to speed up in its expansion forever or not. So that's harder to calculate, but we do have some values.
Yeah, imagine it's like you're trying to throw a dart out and it's going to reach the surface of whatever it is, but like it's just still going and then the surface is still going and it's just until one of you doesn't exist anymore and it's more likely the dart.
Yes, exactly. Okay, so then keeping those things in mind, there are a few different edges that we can talk about. Right, there's never going to be an easy answer. I'm so sorry.
Never.
So one of them is the optical edge, the optical horizon. Where can we stop seeing things? From between about 500 million years to about 1 billion years after the Big Bang happened, this is a period known as the epoch of reionization. Okay, so at this point, there are starting to be stars. They're starting to form into galaxies. And all of the energy from the stars is ionizing the gas around them, and it's mostly hydrogen. So when the hydrogen gas is ionized, when the electron is taken off of the outer shell because it gets energized, then gas clouds don't absorb and scatter light as effectively. So ionized hydrogen is much easier to see through than neutral hydrogen. But that took time to happen. So throughout this whole process, from 500 million years to about 1 billion years after the Big Bang, the universe is opaque. We call this the dark ages of the universe. And
there's always the dark ages everywhere.
And you have to use different wavelengths besides optical light. So you have to use like infrared or microwave or radio light to peer through the dark ages to the cosmic dawn. Okay. But even then, there's a point, the surface of last scattering, where no wavelength of light can observe it. And that's because the surface of last scattering is the earliest source of photons that we can detect in the entire universe. Before that, the photons are trapped. So the seeable edge of the universe is a moment in time, that surface of last scattering, about 380,000 years after the Big Bang. We cannot detect any light from earlier than that.
Wow.
And that surface was created, that signal was emitted, about 13.5 billion years ago, right? However, the particles that emitted that light have been carried away from us because of dark energy. So they are not just 13.5 billion light years away from us. They are you ready?
No.
46.5 billion light years away from us.
No. Mm-hmm. No.
Mm-hmm. Mm-hmm. And that is what we call the particle horizon, the surface of last scattering. That is the observable edge of the universe. We cannot see anything beyond that.
That was a lot of numbers, bestie. I'm going to be honest. And they're really big numbers.
They're really big numbers. Yes. The universe is really big, so its edge, if we can define one, is going to be really far away.
Of course.
As far as we can tell, within that space, there are about 2 trillion galaxies, and the total mass is 1.5 followed by 52 zeros. That number is 150 sextillion kilograms. That's just for regular baryonic matter. If you want to do all of the matter in the universe, including dark matter, there's about 5 to 10 times as much dark matter as there is baryonic matter. So you're looking at 10 times 150 sextillion kilograms of matter in the universe.
They're going to have to start making up new numbers.
They have a lot of these numbers figured out. They do. I think it goes up to 1,000, definitely to 100, and then there are some numbers that have been named up to 10 to the 1,000th power. But yeah, that's what the universe encompasses. Outside the universe, we don't know. Science is math, and math is based on boundary conditions, and our boundary conditions end at the observable, the contemplatable edge of the universe. And so perhaps there's nothing. Perhaps the universe is one of those flat, infinite planes. It will go on forever. Perhaps it's flat but not infinite, and it will close back in on itself. Perhaps outside of it, there's another universe, and we are just one of a multiverse, or one corner of a really complicated geometrical structure that the real universe has. Like, who knows?
Who knows? Not me.
Who knows?
Not me.
And honestly, I think that might be a thing I don't need to know, because I don't know if I could comprehend it properly even if I did know it.
Yeah, for sure. There's definitely it's not like the safety in like you're a speck in like a bajillion things, but it's like the edge of the universe can't scare me because it's already so far away. It's just already so far away that I don't really have to worry. I don't even really have to worry about it. It's just like, that's over there. And that is for the scientists to think about and tell us what they learn about that and how that can make life better here. That's really just all I want to come around to is how do we make life better for other people?
Yeah, exactly. And I, as a person who's very comforted by knowledge, believe that generating knowledge is good for the people. However,
Absolutely.
there are some things like this that I'm okay not knowing.
Yeah.
So I have a fun little game for you,
Okay.
Connie. I'm calling it Beyond the Edge.
Okay.
Some things just aren't meant to be known. I have 5 famous secrets for you.
Okay.
And you know those games on social media where you have to rank them, but you don't know what's coming up?
Okay. Yeah.
Like you only hear them one at a time? We're going to do that. So there are 5 slots here. You have to rank them on a cosmological scale from closest to farthest. So the closest in the number 1 slot, we will observe this. We will learn this secret in our lifetime.
Okay.
Okay. Number 2, that information will eventually reach us, but long after we are gone. Number 3, this is information that you're going to put in the cosmological dark ages. So in order to see it, you would need to use a different light. I don't know exactly what that means in this metaphorical context, but
I'm with
get
you.
it.
Yeah, I do get
Great.
it. Yeah.
Great. Number 4 is Cassandra. It will get to you. You will learn it. It's within the reachable universe. Oh, which I didn't say before. The edge of the reachable universe. Like we could send information there. That's about 15 to 16 billion light years. Okay. So that's number 4. That's within the reachable universe.
Okay.
Number 5, you're saying that's beyond the observable. No one will ever know. I'm okay with this mystery being left to like non-discovery.
Okay.
All right. I have the 5 for you. Are you ready?
Yes.
Okay. The first mystery I need you to rank. Who assassinated JFK?
Can it be like 4, it will get to you, but you can't tell anyone, as in someone knows, but they are not telling? Like, or
Well,
is it
it's you
me
will learn.
specifically? Okay,
You
it's me
specifically will
specifically.
know. Yeah.
Okay, me specifically, I think 1, observe in this lifetime. I feel like a lot of things have been coming.
I'm sorry. You have 4 mysteries left, and you're picking to know with certainty who assassinated JFK? Girl, you don't know what's coming up.
Oh, it's 1 each. Like, I'm not ranking them each on the 5. They all have to
You have to
fit
put these
into
in
the 5.
slots.
Okay. See, that does change the game. Then 2, information will reach us after we're gone.
I didn't know you were that into JFK.
Well, I don't know what else is next, bestie, so I don't know.
I know. Okay.
Okay,
Sure,
give me
yeah.
at the end, maybe I get 1
No.
redo?
Absolutely
no?
not. Nope. I'm being firm today.
Okay.
You can switch it right now before I go on to the next one.
Who murdered JFK?
But the rules of those little social media games is you don't get any switches.
Okay, this is interesting. Because you're pushing for this, so I'm like, okay, that gives me the scale of everything else.
No, I just
Okay.
need you to understand how the game is played.
Yeah, okay.
You can put it at 2.
Okay, I'm going to keep it at 2 then. But then you make a face, bestie.
Well, yes, because that's objectively a mistake, but you've locked it in, so
But
we'll
I don't
continue.
know what else is coming. And I think we will.
And that's
Someone
why
will know.
you gotta put it further down the list.
Really?
Okay, well, the next one,
Okay.
the next secret was there, and what happened to the lost city of Atlantis? You're telling me you almost said you wanted to know who killed JFK more than what happened to Atlantis?
Oh.
That's why I was shocked. So where would you put this?
Oh, I thought it was just like whether I would learn it, not how interesting it is to me.
Well, I mean, those are inherently linked, right? Like the things that are interesting to you, you want to learn more.
But I'm thinking about like things that I just may not learn because like people are not telling us information or they're hiding it or whatever.
I don't think you understand the premise
I
of the
probably
game.
don't then.
There are five. I have for you 5 mysteries. You have to rank these mysteries in order of what you would most like to know.
Gotcha. Okay. Then if I'm stuck with JFK at 2, I will just accept that. I don't know what's next, so I am going to go with 5.
Okay.
Yeah.
We will never, no one will ever know what happened to the lost city of Atlantis, or
Well,
if
now you're making
it
about
existed.
everyone.
Yeah.
And not just me.
Because you can't tell anyone. Okay. So, all right.
Okay.
That's locked in.
Yeah, I'm going to lock it in.
Next, please rank the knowledge of Cleopatra's final resting place.
Then 4. It will get to me, but I can't tell anyone. It's just for me to know.
Your own little personal secret.
Yeah.
Okay. Yeah.
I'm scared for the next 2. Because I know you're also diabolical sometimes, bestie.
Connie,
And we started rough, so I'm gonna accept it.
where would you rank knowing what Zendaya's wedding dress looked like?
Oh, but I don't know what the last one is. Oh,
I'm so evil. I love it.
I'm so upset because I don't know what the last one is, and I don't know if you're gonna go with like something that I would really want to know, or something that I really am just gonna be like, I couldn't tell you. What if I do care about that one less than Kerosene Zendaya's dress?
Actually, before you answer, I feel like, because we didn't say what like the metaphor version of 3 was, but I think this being in the Dark Ages means you can like learn or perceive the answer to this mystery, but with a different, like, you can't see it.
Yeah.
It's with a different sense.
Yeah. Then 3.
Okay. 3. So like you'd be able to like feel it, but you would not be able to look at it.
Yeah.
Okay.
Could someone describe it to me? Yeah, like it's written out in an article, but not like we don't get pictures. I could accept that. Yeah. Okay, what's the last one? What is something that I will learn in this lifetime?
You will learn the ultimate question of life from Hitchhiker's Guide to the Galaxy.
Well, yeah, because don't we all already know it?
What is it? What is it?
It's not 42?
No, that's the answer.
Oh.
So Deep Thought gave the answer to the question, and then the purpose of Earth was to run a simulation to figure out what the question is.
Right. Yeah, I think that kind of makes sense to me, because we are on the Earth living whatever it is. So we can technically observe it. We just cannot name it, perhaps.
True. Well, listeners, whether you've found the meaning of life or not, remember you are space.
Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram, or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm @ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod, or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.